Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I would like to talk about integrative data mining for drug discovery using the semantic verb. As we can imagine, there's now an incredibly rich resource of public and proprietary information pertinent to drug discovery. I have listed some resources taken from the public domain. You can see there has 64 million compounds and 16H3 bioassays from PubChem and 9 million protein sequences from SwissPort and 58,000 3D structures from PDB, and also some other resources from EMBL and PubMed, and also we have emerging pathway, disease gene, and phenotype databases. So with this bunch of information, one of the great challenges for us is how we separate the wheat from the chaff and use of all of this information together to discover the next generation of treatments. So to do this requires a framework of integration that includes semantics, cross-domain data mining, and advanced determination of relevance. At our university, we're tracking this from a compound-centric approach using aggregative verb-service frameworks and semantic data mining and automated mining of journal articles. So this approach is including 4 layers. The first layer, storage. It is a comprehensive information storage, including the semantics and metadata. So we have local databases save such data, and we have information generators like predict models, and we have extraction from journals and network models. So the second layer interface is to create common interfaces to stored information. So we have created cheminformatics verb-service infrastructure. You can find as much as information from our website, chembiograde.org. The third layer is aggregation. We aggregate verb services using RDF and or XML. So next layer is interaction, is to create kinds of software for information access and storage. So we create integrative data mining tools like Windy. As usual, people will always have a same question: what do I need to know about this compound when they have it for the first time? And also the answer to this question will always give them a good point to know about it. And also we know the key insights will often come only when the information from multiple sources is understood in aggregate, and the multiple sources may support or conflict with one another, but either way, the information is very important. So we create this kind of tool, Windy, which is a prototype aggregate data mining tool. It tries to help this question, because it will find no obvious associations between compound and biological activities. So currently, we would like to aggregate 4 main resources. One is just into Windy, so like databases, activity related, and predictions and models, and documents, including journals, and some other verb sources. So all of this just based on verb service infrastructure. So then Windy will provide a tool that allows the researcher to understand the compound, understand the context in which the compound operates, and to find clues to help them understand the properties of the compound. Maybe they were the compound which they might not have discovered before. So Windy will give them just a useful tool to do some research. So this is our Windy version 1 client interface. It will take smiles as input and send these to our Windy verb services. So Windy verb service will do 2 things. One is to do similarity search on our local databases. Another is to call some verb services available on our site. After that, all the results will be aggregated in XML as output. So Windy will process this XML and display the results on the same page. So we have already released our public version through this link. So right now, what we have now is XML, which just can help us to find some relationships between the compound and activities, compound and literature information directly. So we're just wondering if we can find some more inferred relationships based on the XML automatically, it should be more useful. So we convert XML to RDF and create the RDF network to solve this problem. So Windy version 2 is our ongoing project right now. I will talk it later. So right now, I just want to show a little bit gene-disease relationships. We have built gene-disease relationships based on the PhenoPrint, which is provided by Professor Peja from one of our bioinformatics group in our school. So PhenoPrint is a matrix of predictions of genes and disease relationships based on the known relationships mined from literature and machine learning predictions. So this is an example show the experimentally and predicted associations of genes and malignant neoplasm of breast, kind of a breast cancer. So we have a gene and disease relationship as well. So we would like to add chemical disease relationships into Windy as well. So first we do the similarity search to find the similar compounds which are active or inactive in the PubChem bioassays, and to find similar drugs from the drug bag and similar compounds from the literature. Then we can get some text information like descriptions of PubChem bioassays, usage of drugs, and titles of journal articles. Then based on that, we can create two kinds of chemical disease relationships. The first is a directory one. We just take a text searching to find which disease are contained in this text. Then we can just point out the relationships between the compound, query compound and disease. Another, we create the infer one. We use a Go ontology to find which Go terms are contained in this text, and use a Go annotation to find which genes associated with this Go terms, and use a PhenoPrint matrix to find which disease are associated with these genes. Then we can infer the relationships between the query and the disease. So next, I just want to show some cooperating evidence taken from the Windy version 1. We select the doxorubicin as a query compound. Doxorubicin is commonly used in the treatment of a wide range of cancers. So from this text, we can see the doxorubicin is predicted active in NCI H23 by our NCI tumor cell predict models. And also a similar compound with the similarities 0.964 just is to be shown experimentally active in NCI H23 in this particular PubChem bioassay. Also, we can find the non-specific tumor inhibition properties of the doxorubicin is identified by our predict models. And a similar result can be found in the ontologically marked up text in the similar drug, danirubicin. And also the doxorubicin is predicted to have toxicity issues by our tox tree. And it is noted in the ontologically marked up text in the similar drug. This is some insights taken from the literature search. We can identify a well-known leukemia usage from this mainland database search. And also we can find listener known applications of this similar compound, which is against HIV-1 integrase. So from this above of results, we can find the Windy version 1 just provides automated aggregation of information, but it relies on the manual interpretation of these outputs and manual just identification, the conflicting and cooperating evidence. So then we would like to create Windy version 2 to solve this problem. We create a simple O ontology to identify this kind of elements and relationships based on the XML. So we can identify the query is similar to this CID, which is a PubChem compound ID. And this CID is active against this AID, which is pumpkin bioassay ID. And also we can find the breast cancers is contained in this pumpkin bioassay. So the other similar routes can be found out. Then we can just create the RDF network, expand out from the query. Then RDF inference engines can be applied and results can be filtered. So this is our Windy or RDF network. We can find some relationships like the query is similar to this GID, which is a journal ID. And this GID is associated with a journal title and article number. Then we can find the PID, which is a PubMed ID. And we can find the article titles. Also, we can find the query is similar to the CID, and the CID is associated with the AID. And for both of the journal title and the descriptions of the pumpkin bioassay, we can find which glutens are contained in and which gene and disease are related. Then we can find some inferred relationships like query associated with the journal title, query is associated with the disease, and associations between the query and the AID. So then we employ rule-based inference algorithms to retrieve the new relationships based on the RDF network. So I have listed some of the outputs is here. So we can see the query compound is associated with a list of PID and associated with a list of article title. Then we can find the query compound is associated with a list of bioassay. And also for the Windy version 2, we would like to add, we would just find some more inferred relationships based on the RDF network. And we will focus on the query compound and genes and disease relationships as well. Also, we would like to add some advanced algorithms like automated extraction of relationships from the literature, applied to PubMed, abstract, and open access full text. And also, we would like to add advanced concept of similarity and relevance of journal articles, incorporating structure and tautological similarity, and add the wide-scale predictions based on more of validated models and chemical biological AC networks. Then this is my summary. Just based on what we have done, we would like to see the exploiting the complex explosion of public and private data centered on compounds will give a competitive edge for drug discovery. We cannot do this by applying verb-service architecture and semantic verb methods, but it is a very new era. There is a lot of work to be done. And Windy offers a new approach to data mining that across information source types to look at the big picture and to identify cooperating or the conflicting informations from models, ACs, database, and publications. So next is, I would like to thank Sakura, who is working with me to build the Windy version 2, and thanks Lily to fund this project. Thanks Microsoft to give us a prior grant. Thanks Microsoft Research give me this opportunity to print my work here. Thank you so much.
Great. Thank you. So, any questions? Well, I have one, Jan. The Windy platform or software, is that something that you're releasing or will provide as a service to people?
It can use the web service as well, and we also publish the version. You can just use this public version as Windy. I have showed you the link as before. Yes.
Okay. Thank you. Any other questions for Shan?
Oh.
In that case, if I can leave you to do the little shuffle with the microphone. So our last speaker is Mark. And Mark's going to be taking us through the extraction of nuclear magnetic resonance, for those of you that are familiar with NMR, spectra and structural data from documents for semantic representation and reuse.
Yes. He's also going to configure the displays on his laptop.
Configure the display.
I think it's going to work. Do we have a picture?
Yeah, is it on both? Yeah.
Fantastic.
Good. Okay. Mark,
Right. Okay, hello everyone. My name's Mark Borkham. I'm a postgraduate student from the University of Southampton School of Chemistry, and I'm going to talk to you about extracting NMR spectra and structural information from PDF documents on the internet. And we feel that this is a really important problem to solve because there's a lot of legacy data out there on the internet, and it could be curated and put to further use. So I'm a computer scientist. I'm not a chemist. I don't profess to be one, so I'll introduce NMR for people who haven't met it before. Nuclear magnetic resonance spectroscopy is an analytical technique used in chemistry, and it exploits the magnetic properties of certain atoms. The ones that we've focused on are hydrogen, the protons, and the particular 13 isotope of carbon. You'll have to forgive me with terminology. If it's compiler engineering, I'm quite happy to talk for hours, but chemistry... Anyway, so I'm going to show you the objects of interest very quickly. We've got the spectrum itself, which is, for all intents and purposes, a graph, and it has a scale, the spectrum scale, and I've drawn some boxes around it to make it easier to distinguish. And a nice feature of publications today is that people will often put the molecular structure in their data as well. So we end up with this nice graph with an embedded molecule. And the question that was posed is, wouldn't it be nice if we could go back from this to the original data? Now, there's a bit of a problem here. When you publish NMR spectra, or any piece of data really, in a PDF document, what you're doing is making hamburgers. You take your data and you mince it all up, and then you present it as a picture. And that's great. Don't get me wrong. It's wonderful that we have pictorial representations of things, but it's very difficult to use that picture to do more research. You have to ask the person for their data. Sometimes they're reluctant to give it to you, and that's been discussed at length, so I'm not going to go into that. The problems from my perspective are that this data is not machine readable, and so the information, the knowledge that is there, is lost. So how can we go back? So there's this neat quote from Michael Kay, who's a bit of a prolific blogger, and he says that converting PDFs back into XML is a bit like turning hamburgers back into cows. So that's exactly what we're going to do. We start off with the PDF, which is a really nice-looking hamburger, and what we want to do with the PDF is slowly but surely collect all the small bits of information together, group them up into larger bits of information, and then enrich that as XML documents. So what we're left with is a cow. Now, I mentioned compiler engineering. That's exactly how I've approached this project. I don't know anything about the chemistry, but I do know how to write compilers. When I see a stream of tokens going in a row, I look for regularity and grammars. And so what I'm going to show you is how we've applied that to extract this information from PDFs. So what are the features of interest? Well, PDF is a vector format. So you've basically got three things. You've got text, specified as characters. You've got lines, specified as an origin and an extent. And you might have something called a polyline. This is just terminology that's come from PDF documents. And that would be a line with multiple segments. So it's got one origin, and then they specify a lot of extents. And so what I've got is a very simple idea with a bit of maths, because I'm sadistic, is to have a bounding rectangle for any feature. So if we have this bounding rectangle, we can start doing useful things. And if I go back up to the first slide, if you look at the bounding rectangles that I've drawn around the objects, we notice something quite interesting. First of all, where two objects intersect, we can put them in a tree as siblings, and we can assert that there is some relationship between those two objects. Where two bounding boxes, one is contained within the other, we could assert that there's a high likelihood that the child object, the box inside the larger box, is some derivative of the parent. So we can apply this, and what we're left with is an abstract syntax tree, like so. So we construct a load of bounding boxes, and we group them all together using this algorithm, and what we're left with is essentially the document object model, but for chemistry papers. And we've done this inside an extensible framework that I've been building, and it allows us to specify heuristics at the moment to allow the abstract syntax trees to be collapsed into objects. So we can say things like, a graph axis has a very long horizontal line. This is a really powerful thing to be able to say, because it allows us to describe the scales and the spectra themselves in terms of what they look like on a page. So I can start teaching I can teach my compiler essentially how to distinguish between Proton NMR and IR NMR, which is quite useful. So future work that we're going to do is something called an SVM, a support vector machine. What you end up with on each page, if you chop the page up into constituent rectangles, you can do this arbitrarily or apply clever techniques, you end up with a vector. And that vector just has, for each component, a set of numbers. So the magnitude, which would be the number of occurrences of a particular feature, or possibly the orientations of lines if you're looking for molecules. And you can start doing really clever machine learning techniques for this. So hopefully on the next page. Right. So I'll just show you very quickly the work that we've completed. My colleague Bill Brower at Penn State University has done some really clever work to do with approximating the curves that I can extract from documents. So the idea is that what I'm going to do is say, this is a particularly juicy looking hamburger, and I have a good idea of what that hamburger might taste like. And then I can give that hamburger to Bill, and what he's got is brilliant software that uses Gaussian mixture modeling to approximate the curve and give you a good approximation of the original data. And I'm also working on connection tables, which is where you take the molecular structure straight out of the paper. And if you look over here, we can actually distinguish between the stereochemical bonds as well. And we're going to rip the molecules out as CML documents. So you get fully enriched PDF documents out of this. So to conclude, I'm not going to keep you from your lunch. There's a wealth of this information on the internet. And our aim is to make that available to people as CML and or Chem. So any questions, please? I'd just like to thank very quickly Tony Hay and Microsoft for inviting me to talk, the WUN for funding all this work, and the other contributors. And I'm going to have a drink now as well.
Questions for Mark? I'm just curious, nothing illegal about doing things with PDFs?
All the PDFs that we've used for testing are in the public domain. So providing you have permission to use that PDF and to work with it, then what we're doing is no different to selecting all the text and copying and pasting. That information is essentially already there. We're just converting it into another form. We're
That's for the formatting, but the use of the content is different. Interesting issues. Very interesting.
Actually, we're actually working with PostScript. We convert all our PDF documents into PostScript to normalize them, and we find that easier to work with. That does have some other drawbacks, but if you buy me a beer, I'll discuss them with you. But to all intents and purposes, we take PDF documents and enrich them.
Just before I'll come to Tony in a second, I want to make sure I get this question in. So you could potentially use some of the other text mining
Yes.
to identify possible structures, so that when you're trying to resolve them, you triangulate with the in-sheet.
Absolutely.
Yep.
But exactly. We're actually collaborating with Peter Murray-Rust's group in Cambridge, and they've got Oscar and Opsin, which are fantastic text processors that allow you can basically give it a load of character data, and it will extract all of the chemical entities, so all of the molecular names. Okay, some. Okay. Trying to give him some credit.
No,
okay.
absolutely.
So what we're working with at the moment is having a nice framework where anything that looks like text we could give to Oscar to work with, or we could give to any other piece of software. So it's an extensible framework, and anything hopefully will be possible in the future. And we'd love to work with other domains as well. So if you can teach us how to tell the computer what your objects of interest look like, we'd be very interested to work with you and see if our framework can help you enrich your legacy data as well.
I love what you're doing, it's great, I look forward to you on it. I think there's an issue here, not in the PDF format itself, and the fact that maybe the PDFs are open access. I think there may be an issue, hopefully it won't be a problem. For the author, the author's inserting
Yes.
an image, and you're harvesting
Yeah.
data that can now be reused, repurposed, redistributed.
Mhm.
Say, I'm willing to make it freely accessible. Anybody can print it out, they can grab a screen of it, but they will not allow people to download it as a remote data set.
Right.
So I think that could be the issue. Because it's an author issue. They grant the rights
Yep.
to the image, not to the database itself.
We're actually working on a completely separate note, a project called Storelink, and it has another name called Cladia in Southampton. And this is in cooperation with Edinburgh and Reading. And it allows you to do academic trackbacks, essentially. So there's the trackback protocol for blogs where you can say, you know, I've made a comment about your blog post. And we're working on exactly the same thing for citations, for converting data. So you would be able to say, I've downloaded your Spectra and converted it into this. The difficulty is actually in finding out who to send that message to. So we need to work with the publishers so that information is available. When I do the enrichment, it would be nice to tell the person. Currently, all I have is a name, and as you've shown us, it's very difficult to go from the author name to an author identifier in a consistent way.
Other questions for Mark? Okay. With that, I'd just like to thank Mark and